Hello everybody, I'm Hassan Hadi, a student in Computer Science in University of Kufa. In this video I will teach code optimization and compiler design. Optimization. What is the optimization? What we mean when we said optimization and compiler design. The optimization and compiler design is the final stage of compiler. Everything after optimization is done. Though it is optional, not obligatory. This is a program transformation technique which tries to improve the code by making it consume less resource, like CPU and memory, and deliver high speed. In optimization, high-level general programming constructs are replaced by very efficient low-level programming code. Rules of code optimization process. A code optimization process must follow the 3 rules given below. First rule is the output code must not in any way change the meaning of the program. This point is very important. I will repeat it. The output code must not in any way change the meaning of the program. Second rule, optimization should increase the speed of the program, and if possible, the program should demand less number of resources. Third rule, optimization should itself be fast and should not delay the overall compiling process. Efforts of an optimized code can be made at various levels of compiling the process. First, at the beginning, user can change or rearrange the code or use better algorithm to write the code. This is important again. Second, after generating intermediate code, the compiler can modify the intermediate code by addresses calculation and improving loops. In optimization, the whole problems we find it in loops, so the improving loops is very important. Third, while producing the target machine code, the compiler can make use of memory hierarchy and CPU registers. Main types of code optimization. We have 2 types. First, high-level optimization, and the second, low-level optimization. High-level optimization is a language-dependent type of optimization that operates at a level in the close vicinity of the source code. High-level optimization includes inlining, where a function call is replaced by the function body, and partial evaluation, which employs reordering of a loop, alignment of arrays, padding, layout, and elimination of tail recursion. Low-level optimization is highly specific to the type of architecture. In high-level optimization of code optimization, performed fall under intermediate code optimization, which is language independent. This includes, number 1, the elimination of common sub-expression. This type of compiler optimization prepares for the instance of identical expressions by evaluating to the same value and researches whether it is valuable to replace them with a single variable which holds the computing value. Number 2, constant propagation. Here, expressions which can be evaluated at compile time are identified and replaced with their values. Number 3, jump threading. This involved an optimization of jump directly into a second one. The second condition is eliminated if it is an inverse or a subset of the first, which can be done effortlessly and single pass through the program. A cyclic change jump are followed till the compiler arrives at a fixed point. Number 4. Loop invariant code motion. This is also known as Haussitting or scalar promotion. A loop invariant contains expression that can be taken outside the body of a loop without any impact on the semantic of the program. The above mentioned movement is performed automatically by loop invariant code motion. Number 4. Dead code elimination. Here, as the name indicates, the codes that do not affect the program rules are eliminated. It has a lot of benefits, including reduction of a program size and MSCA IVSIM script compiler design running time. It also simplifies the program structure. Dead code elimination is also known as DCE, dead code removal, dead code stripping, or dead code strip. Number 6. Strength reduction. This compiler optimization replaces expensive operations with equivalent and more efficient ones, but less expensive. For example, replace a multiplication within a loop with an addition. In low-level optimization, this includes the following. Number 1. Register allocation. Here, a big number of target program variables are assigned to a small number of CPU registers. This can happen over a local register allocation or a global register allocation or an inter-procedural register allocation. Number 2. Instruction scheduling. This is used to improve an instruction level parallelism that in turn improves the performance of machines with instruction pipelines. It will not change the meaning of the code, but rearrange the code of instruction to avoid pipeline stalls. Semantically ambiguous operations are also avoided. Number 3. Floating point utilization. Floating point util are designed specifically to carry out operations of a floating point number like addition, subtraction, etc. The features of these units are utilized in low-level optimization, which are highly specific to the type of architecture. Number 4. Branch prediction. Branch prediction technique helps to guess in which way a branch function, even though it is known definitively, which will be of great help for the betterment of results. Number 5. Behavior and profile based optimization. Behavior optimization technique is carried out over small code section at a time, or to transform them by replacing with the shorter or faster sets of instruction. This set is called as a behavior. Profile based optimization is performed on a compiler which has difficulty in a prediction of likely outcome of branch size of arrays, or most frequently executed loops. They provide the missing information, enabling the compilers to decide when needed. Optimization can be categorized into two: machine-independent optimization and machine-dependent optimization. Machine-independent optimization phase tries to improve the intermediate code to obtain a better output. The optimized intermediate code does not involve any absolute memory location or CPU registers. Machine-independent optimization is done after generating of the target code, which is transformed according to the target machine architecture. This involves the CPU on register and may have absolute memory references. In machine-dependent optimization, the compiler takes and the intermediate code transforms a part of the code that does not involve any CPU register and or absolute memory location. For example, this code do function, and the statement of do function is item equal 10, value equal value plus item, while the function of while is value less than 100. This code involves a repeated assignment of the identifier item, which if we put this way, item equal 10, do function. The statement of do function is value equal value plus item, while the condition of while is value less than 10. Machine-dependent optimization is done after the target code has been generated and when the code is transformed according to the target machine architecture, as we said before. It involves CPU register and may have absolute memory references rather than relative references. Machine-dependent optimization bit efforts to take maximum advantage of memory hierarchy. Machine-independent type. We have two types: function receiving and loop optimization. Function receiving. The first one in function preserving is common sub-expression elimination. The expression that produce the same result should be removed out from the code. For example, A equal B star C plus G, D equal B star C star E. It may be worth transforming to the code to identifier. We named it TMB, a shortcut for temp. TMB equal B star C, A equal temp stars G plus G, D equal temp star E. Number 2, constant folding. If expression generates a constant value that instead of performing its calculation again and again, we calculate it once and assign it. For example, integer fold, the function or the method integer fold, the statement of it is return 3 plus 5. The expression 3 plus 5 can be evaluated at compile time and replace it with the constant 8. So rewrite it as integer fold return 8. Number 3, copy propagation. If one variable is assigned to another we replace uses of the assigned variable with the copied variable, and we need to know where copied of the variable propagate and interact with the scoping rules of the language. For example, x equal y. If x larger than 1, then x equal x star f of x minus 1. That's rewriting. We rewrite that to x equal y. It's the same. If y instead of x, we write now y. If y larger than 1, then x equal again y star f of again y minus 1. Number 4, dead code elimination. Dead code is one or more than one code statement, which are either never executed or unreachable, or if executed, their output is never used. Thus, dead code plays no role in any program operation, and therefore it can supply to be elimination. For example, x equal y star y in statement, then x equals z star z. When we replace the value of the identifier x to z star z, we will never need x equal y star y, so we will eliminate this one. Loop optimization. We are going to perform optimization on loops to code motion, strength reduction, frequency reduction, loop distribution. The first one is code motion. It specifies on a condition if we perform some operation to be carried out and then compare for a condition instead of that perform and calculation outside the loop and assign a value in the collocation. For example, while I less than or equal limit minus 2, we rewrite it to t1 equal limit minus 2, then while I less than or equal t1. Strength reduction. It is specific. The operations such as multiplication and division can be replaced by addition and subtraction. Specifically, the multiplication operator can be easily replaced by left shift operator, and the division operator can be easily replaced by right shift operator. For example, t1 equal a star 2, and the second example is t1 equal a division 2. t1 equal a star 2 will rewrite it to a left shift operator, double left shift operator 1, and the division is a double right shift operator 1. Frequency reduction. In this case, if an expression inside a loop is not dynamically affected by a loop, we calculate it outside the loop and use the value inside the loop. For example, while y less than or equal limit, the statement of while is t1 equal a star 4, t2 equal I star t1. The line t1 equal 1 star 4, it's the same in whole loop. It's the same. So we will outside it out to be rewritable, and we will write it to t1 equal 1 a star 4, while I less than or equal limit. Statement of while is to t2 equal I star t1. Loop distribution it is the final one. It specifies the values in a particular loop to be assigned to an array keeps of varying, like the array location in which a loop need to be worked again and again. We can use two different loops, which allows loop distribution. For now, we will end the code optimization. I hope the interest has passed. Goodbye.